In the last lecture, we have seen that if I have function f from an open connected set Rn to Rn to Rm and x naught is a point, then candidate for df at x naught in the matrix form, also written as Jacobian matrix, is equal to this matrix, right, del fi del fj I equal to 1 to m, j equal to 1 to n, and in particular case m equal to 1, this df x naught is a special notation I have for that, that is called grad f. This is simply this vector del f del x1 del f del x2 del f del xn, and we have worked out two examples for n equal to 2, m equal to 3 and n equal to 2, m equal to 1. But each time what we have to do, we first come up with these candidates, we calculate these quantities del fi del xj and then actually verify the definition, that is we put norm h E x naught h equal to f x naught plus h minus f x naught minus d f x naught h and show E x naught h goes to 0 as h goes to 0. That is what we do or we did. So, each time we come up the candidate, I have to check it. Now, that is a lot of work. So, we must come up with some criteria to check that once we calculate this, we are able to say somehow that is differentiable or not, instead of checking this, because checking this means writing down everything here, f of x naught plus h, f of x naught, d of x naught h, and then actually checking this. So, today's lecture I will prove one criteria which is very useful, and we actually use it every time to check differentiability of a function from looking at the candidate for Jacobian. How do you do it? Well, first I give you an easy exercise and you must verify it from the definition, and then I write it the criteria. First exercise is this. So, suppose I have f, same setup, u from Rn to Rm and x naught is a point in u. I want to check the differentiability criteria at x naught. Well, I can write, I know f as m components function where each fi is from u to r, right. The statement of the exercise says f is differentiable at x naught if and only if each fi, this u from r, now this real valued function, is differentiable at x naught, and importantly the Jacobian matrix of f at x naught is precisely this matrix. This is a row vector having n component each row has n component, del f1, del x1, del f2, del f1, del x2, so on. So, this is a m cross n matrix, of course. So, it boils down to checking. So, checking differentiability of f from Rn to Rm boils down to checking component wise real valued functions fi, they are differentiable, and this is the relation. Okay. And you see the Jacobian matrix will be from this description, Jacobian matrix will be exactly this. The criteria is each fi is differentiable. This is very easy exercise. So, you verify it from definition again. Once you verify, you can use it everywhere. Now, let me state the criteria for differentiability. So, I actually have to state the criteria for differentiability of real valued function. So, let me write the statement clearly and then do the derivation. Let me put it as a theorem. So, U in Rn, let me write it is theorem format, open, I do not need connectedness here actually, open f from U to Rm and x naught is in U. Suppose d1 f x naught d f x naught exist, okay, where d I f x naught is a directional derivative with respect to, let us say, canonical basis, that is d E I f at x naught, directional derivative in the direction E I, and okay, there are n many, they must exist first of all. If they do not exist, there is no question of f being differentiable, and for any choice of I1, I2, I n minus 1 from 1 to n. So, you have n many here, you choose any n minus 1, and I have for this d I1 f, d I2 f, d I n minus 1 f are continuous. At x dot, then f is differentiable at x naught. So, let me explain it here. So, suppose I have f from U to Rn, x naught is a point, f I write this way, okay, fine. Now, what I first need? I need, for what is the theorem says, that if I look at d I f x naught, which is limit h going to 0, f of x naught plus h E I minus f of x naught divided by h, this exists for I equal to 1 to n, and choose I1, I2, In minus 1, any between 1 to n minus 1. So, let us say I1 equal to 2, or say I1 equal to 1, I2 equal to 3, I3 equal to 4, and In minus 1 equal to n, or any other choice 2, 1, 3, 4 n, or 2, 3, 4 n, or 1, 2, 3 n minus 1, any choice. this d I k f is continuous at x naught. Then I can conclude f is differentiable. Once I have that, then the verification becomes actually easy. This is no longer exercise, this is what I am explaining here. Okay. But anyway, whatever you state as a theorem, you need a proof. So, for today's class, let me prove this theorem. The proof is not that important, but it is a prototype of the proof what one does in several variable calculus. So, once you know it, you can write down yourself, but at least you should see it once. Well, let us see proof. First remark, from the earlier exercise, it is enough to as proof for f real valued, that is m equal to 1, because after all I can break down the in components. So, every statement is true component wise, and each component is differentiable, then the function is differentiable. So, this is the first deduction I made, okay, just to make the proof easy. So, let us assume f is real valued, so I have only grad to consider. Exist and any n minus 1 of them continuous. So, I assume del f del x2, del f del x3, del f del xn, so exist at x naught, continuous at x naught. You may say why I have chosen x2, x3, xn. It could be x1, x3, xn or x1, x2, xn minus 1, well, it does not matter, because you see after all ei's are coordinate, these are the directional derivative with ei's. Now, which one I call u1, which one I call e2 does not matter, I can make a rotation and I may call e1 e2 or e2 I call e4. So, how do you name the coordinates, it does not matter. It means to say that okay, you have x axis and y axis like this, horizontal axis is x and vertical axis is y. So, you just do what, you turn the paper 90 degree, the y axis become horizontal, x axis become vertical. So, you call the x axis y axis, y axis x axis, so it does not matter. So, I can choose without loss of generality that x del f x2 to del f x1 continuous. Okay. Now, x naught is in u is open. So, there exists a delta such that if I take a ball around x naught of radius delta, this is completely in u, correct. Okay. Let us take any h such that norm of h is less than delta, that is to say x naught plus h, this is also in b x naught delta, so is in u. So, I have to be in domain everywhere to check, because f is defined only in u. Of course, I can write h equal to h into u, where u is h by norm h unit vector and h is just norm h, which is less than delta. So, u is a reductional vector, and I can write u since I have chosen the basis u1, u2, en, I can write u as u1, e1, u2, un, en, where u1, e2, en just canonical basis. This is the basis with respect to the gradient is calculated. Let us continue on that board. I have to write what is f of x naught plus h minus f of x naught. This is actually f of x naught plus h u minus f of x naught. I write it a little bit tricky way, so that I can use my assumption. I write it in this way: f of x naught plus h u1 e1 minus f of x naught, okay, plus f of x naught plus h u1 e1 plus h u2 e2 minus f of h x naught plus h u1 u1 so on f of x naught plus h u1 u1 h u2 e2 h un en minus f of x naught plus h u1 u1 h un minus 1 en minus 1. What I have done? See, this term is extra, but this will get cancelled here. This term is extra, this will get cancelled in the next term. So, finally, the term remains is this minus this, which is f of x naught plus h u minus f of x naught. So, I have put inside certain terms in a way that in each of the component of this sum only one coordinate is varied. Here this direction is the directional derivative with, it will come a directional derivative with respect to u1. Here it will come h of u1 u1, h of u1 u1, only u2 u2 comes, second derivative will come. So, I can write it in this form. Let me write it in a compact form: k equal to 0 to n minus 1, right, yeah, f of x naught plus h v k plus 1, or k equal to 1 to v k, let us say v k minus f of x naught plus h v k minus 1, where v 0 is 0, v 1 is h not h u1 u1, v 2 is u1 u1 plus u2 e2, so on. v k is v n is u1 u1 u2 e2 un en. Now, I will use differentiability and continuity. Let us, I will assume that these exist and these things are continuous. K equal to 0. What is the term? X naught plus h e1 h u1 e1 minus f of x naught, which is del f del x1 at h u1 plus error term h u1 e x naught h u1. So, this is really h into del f del x1 at u1 plus h u1 e x naught h u1. This term goes to 0 as h goes to 0. No, I should have k equal to 1, sorry, not 0, okay. K equal to 1, please. Now, for k greater than equal to 2, f of x naught plus h v k minus f of x naught plus h v k minus 1, this I write f of x naught plus h v k minus 1 plus h u k e k minus f of x naught plus h v k minus 1, which is f of some b k plus h u k e k minus f of b k, where b k equal to x naught plus h v k minus 1. Now, here I can apply, this is real valued and I will prove it, do not worry, just simply mean value theorem. I will prove mean value theorem for functions of taking value in R or Rm, but you can think of it as a mean value theorem because you are just using one variable here. This will become del f del x k at some z k with the difference which is h u k, where z k is in b k, some number in b k plus h u k e k. So, this is I am applying mean value theorem. Now, continuity will apply. It will tell you del f k del x k z k is actually del f del x k at x naught plus some E h, where E h goes to 0 as h goes to 0. Okay. So, finally, we put down everything and see what happens. So, you write it. So, I just jump one step, you verify it yourself that I can actually write f of x naught plus h minus f of x naught equal to summation h u k del f del x k at x naught k equal to 1 to n plus h u is norm 1 k equal to 1 to n h k e h. Maybe I should write E prime h or E 1 h. So, E k h, E k h, E 1 h is E x naught h u 1 and E k greater or equal to 2, E k h is those that E k, this here a k should have been added E k h from that, and this as h goes to 0, this goes to is as you see grad f x naught, this is u k, sorry, this is u k dot h, because the other term will go to 0. So as E h summation k equal to 1 to n u k e k h goes to 0 as h goes to 0. H goes to 0 is h is norm of h. So, that is the proof for the theorem, and we have a criteria. Thank you.